The Advanced Photonics is a new journal, and it is a highly selective open access international journal for fundamental research and applied applications in photonics and optics.
Advanced Photonics will cover all areas of optics and photonics research, be it fundamental research or applied research. The only thing we are looking for is a new idea, interesting idea, which could have impact on either optics in general or some particular photonic application. We hope very much if you work in optics and photonics and you have one of the best ideas of your life, submit this idea to Advanced Photonics.
Good afternoon, everyone. It's AP live streaming time again. And today we are very pleased to have Professor Ozcan from UCLA to give a presentation about his recent work on AP about the diffractive optics. And before the presentation, I would like to spend a couple of minutes to give a briefing about the journal. AP, as you may know very well, it is a journal kicked off in 2019, in September 2019. And the journal is targeting about the cutting edge papers from the leaders in optics and photonics in the world. And we luckily received the index in 2021. That means we have the first impact factor received in June 2022, which was at 13.5. And last year, we received our second impact factor, which is about 17.3, and ranking top 4 among the 100 JCR optics journals. And this coming June, we are going to receive our third impact factor. Hopefully, it will be slightly higher than 17.3. And the journal was co-chaired by Professor Anatoly Zayas of King's College London and myself. And this is the editorial board, the journal. And these are the famous well-known experts, and you may know them, some of them very well. And as I mentioned, we started the journal about 5 years ago. So in the last 5 years, in each year, we publish one theme issue on hot topics. For example, in the first year, we celebrate the laser for 60 years of the advancement. And in 2021, we have a theme issue on the quantum technology. And 2022, we have a issue on the photonics, the thin film lithium niobate. And 2023, we celebrated the 30th anniversary of the orbital angular momentum. And in this year, we are going to publish one special issue about the AI and photonics. And about 1.5 years ago, which is about September in 2022, we launched another sister journal, which is called AP Nexus. This journal was co-edited by Professor Zayas and Professor Chen Weibiao from the Shanghai Institute of Optics and the Fine Mechanics of CES, together with myself. And this sister journal is targeting some more advanced in technology and engineering in photonics, and we are trying to target the journal for impact factor between 6 and 8. And due to the sibling journals between AP and AP Nexus, so we have a faster transfer between the two journals. And these are the members of the AP Nexus editorial board. And we have currently we have 36 members of the board, and you may know some of them, and they're quite well-known expert in various areas. So we are going to expect your submission of your excellent research result to the AP and AP Nexus, and we are going to keep our impact factor as the top of the optics and photonics publications in the world. And before I hand it over to Professor Ozcan, I will spend a little while to give an introduction of Professor Ozcan. Dr. Ozcan is the Chancellor Professor and Chair Professor for Engineering Innovation at UCLA and HHMI Professor with the Howard Hughes Medical Institute. He is also the Associate Director of the California NanoSystems Institute. Dr. Ozcan is elected as a Fellow of the National Academy of Inventors and holds more than 70 issues and granted patents in microscopy, holography, computational imaging, sensing, mobile diagnostics, nonlinear optics, and fiber optics. And he's also an author of one book and a co-author more than 1,000 peer-reviewed publications in leading scientific journals and conferences. And today's presentation will be based on his recent article published on AP about optical information transfer through random unknown diffusers using electronic encoding and diffractive encoding. So I will hand it over to Professor Ozcan.
Well, thanks for having me. Let me share my screen.
Yeah, finish my sharing.
Okay. Do you see the slides that I'm sharing?
Yes.
All right. So let's see. Okay. So as I'm moving the cursor, do you see that as I'm moving the mouse? Okay, let's see. I guess now.
Yeah.
Do you see the laser?
Yeah,
do you see the laser pointer?
Laser point. Yeah.
All right. Well, thanks for having me. If my audio is not working, please let me know so that I can turn off my camera. You can also see my camera all fine. Is that right? My video?
Yeah, I can see your video.
All right. Thank you. So today I'll share with you some of the work that we have been doing on diffractive information processing and computational imaging. So this work is about diffractive networks, diffractive optical networks, diffractive deep networks. It's based on engineering light-matter interaction within a volume for computing. And this framework that I'll describe to you in the next several slides is good for statistical inference, computing with the speed of light, finishing classification tasks, for example, in a few tens of picoseconds. It's also great for building computational cameras. Probably I'll spend half of my time on the use of diffractive computing for building computational camera systems. And it's also a beautiful framework for inverse optical designs, for solving inverse imaging problems or inverse optical component problems. So a diffractive deep neural network or diffractive optical network is composed of several successive layers, which could be in transmission and or in reflection mode. And the training is done in a computer for a given task. Once the training is done, inference is all optical. For example, what you see here is a diffractive processor where at half a wavelength scale, at every layer, we're optimizing the phase profile of the layer, following another layer, so that through diffraction, we can compute a certain input-output relationship. So the major advantages of diffractive processors is that computation is happening in a passive light-matter interaction, which means it's low power, except the illumination and detection power. Computing through the diffractive volume does not cost us power. Also, it finishes off the task it's given at the speed of light propagation through very thin optical elements. It doesn't mean signals propagate at the speed of light. It means the computational task is completed as the light travels through 100 lambda, maybe 50 lambda thickness of a material. And that could be a few tens of picoseconds, depending on your wavelength. So low latency, and they're scalable. We can fabricate these diffractive processors and scale up our computing. So this is actually a diffractive system that controls the secondary emission of spherical waves in a volume. And you can think of every diffractive layer by controlling the phase element at half a wavelength. It's actually controlling the phase of these spherical secondary waves and creating a super waves through which we compute based on the input radiation. These diffractive systems accept the output plane. They are linear in diffraction, but there is depth to their architecture, which means a given number of degrees of freedom that you have, if you divide it into multiple layers, they learn and perform better through light-matter interaction. I'll give you examples of that. And also, I'd like to emphasize that you can do nonlinear encoding at the input plane. For example, you can encode the information in the phase channel of the input coherent light, and that could give you additional boost through nonlinear encoding of information through the phase channel. So it's actually a platform that we have been playing for various different applications. Various different results that I'll show you today will be coming from terahertz waves because these diffractive processors are relatively easier to fabricate with these terahertz longer wavelengths. For example, this one is a diffractive processor operating at terahertz wavelengths. And you have here about 5 diffractive layers, and there's a topology in each of them where at half a wavelength scale, we control the phase of these layers optimized for a certain task. In this design, you have in total something on the order of 200,000 features engineered and fabricated. Once it's fabricated, this system actually acts like a classifier, which means if you shine light through a new, for example, handwritten digit 5, most of the photons are routed to a detector that is pre-assigned for that class. This is not memorizing just a few different digits. It's not a memory. It's actually generalizing to what it means to be a handwritten digit 5, handwritten digit 7, etc. Because these processors are coherent processors, you can actually encode the information in the phase and or amplitude channels of input information. For example, these are never seen before MNIST handwritten digits encoded in the amplitude channel. For example, if you shine light through this number 7, for the first time, never seen before, for the first time, it's going to be routing the photons to this detector, which alloptically infers the class of the object. Without digitizing, without creating an image, uploading it to a GPU, etc., you can do alloptical computing. These are experimental results coming from the previously shown 3D printed, 3D fabricated diffractive processor. You can also encode the information at the input aperture in the phase channel. For example, this one is a fashion MNIST classifier using a diffractive processor where the input objects were encoded in the phase channel. So a diffractive processor, except the nonlinear detection at the detector plane, is linear. However, phase encoding is nonlinear. And essentially, it's a very powerful way of increasing the inference accuracy of a diffractive processor. These are fashion products also composed of 10 different classes: sneakers, trousers, bags, etc. And the goal here is not to memorize, to generalize what it means to be a trouser, what it means to be a sneaker, bag, etc. And these are some experimental results from never seen fashion products before. this time represented in the phase channel, giving you some beautiful inference. For example, this one is addressed, routing the photons to the correct detector, giving you all optical inference within a few tens of picoseconds of travel time through these thin diffractive processors. These are actually fairly competitive in terms of their inference performance. For fashion analyst products, never seen before, you can push the accuracy something like 92% when you do phase encoding. Arguably, a better way to describe a diffractive processor is a universal linear transformer, which means at the diffraction limit between an input aperture and an output aperture, you can execute all optically any arbitrary linear transformation that is complex valued with a certain amplitude and phase profile. Another way of stating the same thing is that you can have spatially varying point spread functions that are at the diffraction limit encoded between a certain input aperture and an output aperture. And the rule of the game for this success of this approximation is enough degrees of freedom in the diffractive layer. If you have diffractive features, number of diffractive features surpass the space bandwidth product at the input times the space bandwidth product at the output, you have a beautiful approximation power. That means this network can approximate any arbitrary spatially varying point spread function set in the complex domain if you have enough degrees of freedom. However, if you are to the left of this red dashed line, you don't have enough degrees of freedom. You can still have a beautiful approximation if and only if you have a deeper architecture, which means if you give me a certain number of degrees of freedom, a better architecture is create depth in dividing those degrees of freedom into one layer following another layer following another layer. Let me give you a concrete example of how deeper is better in terms of architecture. Let's look at this complex value transformation where this is what I'm trying to approximate. This is defining the spatial variant points that functions between the input aperture and the output aperture. And I only have, let's say, 7.2 thousand diffractive neurons available in this black box. Because this is not sufficient, 7.2 thousand is essentially not sufficient degrees of freedom compared to the space bandwidth product at the input and output, I make a lot of approximation errors, as you can see in the errors of the amplitude and phase. Well, if you take actually a cut at the degrees of freedom and still from 7.2 thousand to 6.4 thousand, but this time distribute them equally across 4 different layers, you get a beautiful approximation, as you can see with the color bars here, where both amplitude and phase are approximating this function very accurately. It shows you the depth of this architecture, which physically you can understand as balancing the power imbalance between ballistic photons and high spatial frequencies. Deeper architectures can balance the power between ballistic photons and scramble them to make essentially more room for higher spatial frequencies to interfere at the output in a correct way. So, by the way, this is not just true for a few input complex fields. These transformations are true for infinitely many complex fields. So it's generalizing a linear complex value transformation. Besides coherent light, you can also program these diffractive processors to execute different transformations at different wavelengths. And you can do this multiplexing without dispersion engineering. That's essentially perhaps the most intriguing feature of diffractive processors. If you want to have, let's say, a few hundred different transformations executed at the same time at different wavelengths, you don't need to engineer dispersion. You need degrees of freedom, which means number of diffractive features within that black box. If you want to multiplex with wavelength, it actually scales with the number of wavelengths. The more degrees of freedom you put in there without dispersion engineering, you can actually approximate them. We've shown that in this advanced photonics paper, actually, that a few thousand linear transformations can be approximated if you give sufficiently large degrees of freedom to that diffractive processor. And we've also shown that these conclusions are independent of the refractive index and material dispersion. In fact, we are using free space kernel as the wavelength multiplexing channel for us, not the materials refractive index. So this is essentially a very important conclusion, which means we can program diffractive processors for temporally incoherent light. and also spatially incoherent light. In a recent work, we've shown that you can actually program universal linear intensity transformations to be approximated using spatially incoherent diffractive processors. And there are various different ways to program these. This was a paper that we published in LSA in 2023, which basically tells you that the diffractive processor and its response under spatially coherent light and spatially incoherent light is actually related to each other by an intensity operation, which means the spatially varying point spread functions of a diffractive processor translate into spatially varying intensity point spread functions in the incoherent domain, which means you can actually take a diffractive coherent processor and use it as a proxy to design different universal linear intensity transformations. That's the teaching of this paper. So this was a brief introduction to give you some of the terminology of diffractive visual computers. So you may be wondering, hey, how does this compare with integrated photonic circuits, where you have these beautiful Mach-Zehnder interferometers and you can do chip scale processing? Well, that's an apple, this is an orange. It's not even to be compared. An integrated photonic accelerator for example, linear transformations is only applicable if the information is in the digital domain. If the information is in the analog domain, like for example, the phase of a scene, that is a two-dimensional or three-dimensional quantity. And you cannot feed that directly to a Mach-Zehnder line because you need to do first phase retrieval. Therefore, if the information is in the analog domain, the phase information, the amplitude information, the polarization information, the spectrum information of a scene, analog processing with diffractive processors in front of a focal plane array or a CMOS is very fast. It executes the task at the speed of light. And before an integrated photonic circuit can access phase retrieval, we're done with our computing. So that's a different domain. If the information is in the digital domain, they win because diffractive processors will not fit into a computer, digital computer, but they could actually be forming hybrid computers, whereas diffractive processors are visual processors. So we've been playing with diffractive processing for various different applications. For pulse shaping, for looking into sensing using terahertz, you can see through opaque objects that are for visible, infrared, opaque, so you can see through packages and understand defects, as we've shown in this paper. Arguably, in my opinion, the most exciting application of diffractive processors is actually in microscopy, in phase imaging. We've shown that you can transform phase information in a quantitative manner into intensity information and do QPI, quantitative phase imaging, directly with light matter interactions. And they're also great for image encryption, performing all kinds of transformations. And even we've shown that you can do multispectral imaging in a snapshot. You can think of a diffractive processor as also a spectral filter that has spatial multiplexing capability, and many others. So today, in the interest of time, I won't go over all of these applications, but I'll share with you the utility of diffractive processors for building computational imaging systems. A diffractive processor is a superset compared to a lens or any form of imaging system formed by traditional spatially invariant point spread functions. So in this superset with spatially varying point spread functions, you can actually execute various interesting tasks all-optically. I'll give you an example from computational imaging field and solving an inverse imaging problem that is frequently encountered for various different applications. Think of this problem where you have an unknown object, you do not know the object, and it changes constantly. It's completely hidden behind a phase diffuser, random phase diffuser, and this random phase diffuser also changes constantly without your knowledge. We want to create a diffractive processor here that's going to formulate the image a few tens of picoseconds diffraction through this thin volume and solving this inverse imaging problem all optically. If you don't have a smart imaging system, you will see just speckle patterns. We want to do this all optically, which means objects are unknown, constantly changing, never seen before. Diffuser is dynamic, random, and I don't know how it's changing, evolving. If you don't do anything smart, this is what you get, speckled patterns at your camera, and I want to instantaneously reconstruct them through light-matter interactions. How do you solve this problem? This was published in eLight, a journal that we've established, which is going to receive its first impact factor this year, which is going to be fantastic. So to train a diffractive processor so that it can see through random diffusers, you have to give lots of examples. This is the learning phase. Through, let's say, 100 epochs of learning, we are giving, let's say, a few thousand examples of random diffusers and random objects. With a structural loss function, we're penalizing and optimizing the diffractive features of the diffractive network at half a wavelength period till it acts like a volumetric filter, filtering out the random phase perturbations of the phase diffuser and giving you a stable image. After the training, we take that diffractive design, fix it, and show new objects never seen before, new random diffusers never seen before. And we expect the reconstruction to happen at the speed of light propagation through a thin optical element, very thin optical element. The spacing is less than 3 lambda, and that gives you the speed of reconstruction. Anything that you see as B, B1, B2, B3, these are new diffusers never seen before. Anything with K, K1, K2, K3, these are diffusers that we use through the learning process. At the end of the game, there's no performance difference between known diffusers that we've seen before or blind diffusers never seen before. And that's the signature of a converged model. So there's some beautiful physics behind this. I'll come back to how this is working. There's no magic here. It's actually all physics induced. And there's an inspirational design here that you will soon hear from me. So first of all, this diffractive processor was designed with MNIST, randomly selected handwritten digits. Now I'm testing it with gradings of various different periods. So that's actually external generalization, meaning that the data distribution of these gradings, they were not represented in the training set because this is the first time that I'm showing gradings. And random diffusers, through them, we can stabilize the image, form some beautiful reconstructions. And if you look at the resolution test period, it's nicely matching with what we put at the input. So it's externally generalizing to different types of objects. We've also experimentally tested this with diffractive processors that are 3D fabricated. This is actually a 4-layer design. This is the 3D printed diffractive layer. It's composed of 4 layers. You see the first layer here. The others are into the board. And there's some beautiful physical insight that I'll share with you in the next couple of slides. But these are some experimental results of unseen test objects never seen before, tested through blind diffusers never seen before, quantifying nicely the gratings and reconstruction of the objects achieved. In fact, this system does not overfit to the presence of the diffuser. After its training, which was always using a diffuser like this, which is a random diffuser. If you take out the diffuser, look at this reconstruction, it gets better. That's expected. If it's a physical imaging system without the presence of diffuser, it's going to be only better. And yes, it is only getting better without a diffuser. So it's not overfitting to the presence of a diffuser. In fact, if you change the correlation length of the diffuser, so this is a random diffuser, never seen before, it works beautifully well. But let's say to confuse our system, you've made the diffuser a smaller correlation length, a finer random grading of phase. Well, still it works. Of course, you sacrifice some resolution, but it works. All of these suggest that this is learning how to image and how to filter out the perturbations coming from these random diffusers. And this is actually, there's some beautiful physics of how it's working. To understand how or what kind of physical processes are behind the success of these diffractive filters, you got to first understand how it works. If you were to take the same diffractive processor and train without any diffusers. If you train it without any diffusers, the topology of the phase islands, one layer following another layer following another layer, completely different. It gets completely different. If you zoom into one of these layers, you see the emergence of microlenses. So these are axially self-aligned microlenses. From the first layer to the next layer to the next layer, these are self-aligned. That's how it images input plane to the output plane through diffraction between the layers. This is communication through these self-aligned microlenses. What happens when you start training the diffractive processor with random diffusers in between the object and the diffractive layer is that you still see the same microlens pattern, but this time opening up space, which means there is some random looking but very rapid smart grading that filled up the space between these microlenses. And that is your volumetric phase filter that takes the modes of the random diffuser and scatters them out. If you look at these layers, first layer to the last layer, you can isolate these microlenses. By and large, they're self-aligned, following axially the first layer, the second layer, and the third layer, and so on and so forth. However, if we just retain these microlenses that are volumetrically aligned, it won't work, because retaining the microlenses and erasing everything else doesn't work. If you get inputs with random diffusers like this, you just get speckle patterns. You cannot reconstruct. Only if you fill around these microlenses with the correct phase gradings in 3D, you can actually start to filter out the garbage modes coming from these random diffusers and retain the modes of the input object and maintain an image reconstruction like this. These are all optical reconstructions with a very fine correlation length of 5 lambda in terms of the phase perturbations, random phase perturbations, and it's the collaboration between these microlenses and the surrounding 3D phase grading that gives you this stability in terms of the reconstructions. In fact, we have taken these ideas to even next level, and we've created a system that can use a single pixel to classify objects, unknown objects, through unknown random phase diffusers with just space to spectral transformation. A good thing about a diffractive processor is, as I've briefly mentioned at the beginning, they can approximate independent universal linear transformations at different wavelengths. Therefore, without any dispersion engineering, you can take different types of objects and create different spectral fingerprints out of them that can be resilient to random phase diffusers. In this example, the spatial features are completely washed away at the spectral band that we use for a given random phase diffuser. However, this single pixel detector is actually trained with this diffractive processor to pick up a spectral fingerprint, which differentially encodes the class of the all-optical input object. And this means you can do all-optical image classification through unknown random diffusers with a single pixel diffractive network. This actually works beautifully well. You can achieve close to 88% through random new diffusers never seen before, classifying random new objects never seen before. If you take out the diffusers, the system works beautifully well, more than 96% classification for m-ness digits. This shows you that it's actually generalizing very well, and it's not overfitting to the presence of diffusers. It works as a classifier, but mitigates the randomness of the diffuser. So there's some beautiful physics behind these systems in terms of how they work. In this case, through space to spectral fingerprint conversion through random diffusers. Another example that I want to share with you is designing some exotic cameras. In this case, we're going to be looking at class-specific diffractive cameras. The goal here is to decide on what to image and what not to image. So think of a scene where there's only one type of object, one class of object that you're interested in seeing, digitizing. Everything else you want to erase. This kind of a diffractive processor with a spatially variant coherent point spread function is going to be acting like a mode filter. All optically, it's going to erase unwanted objects and only retain a distant image of the wanted class of objects. To design something like this, you got to be smart in terms of engineering the loss function, because deep learning-based diffractive designs are very powerful. They can cheat and give you sometimes rotated or stretched versions of the undesired objects appearing here, breaking your structural loss terms. So you don't want to see a rotated or stretched version of these unwanted classes. So that's why we have done some engineering here for the loss functions to erase them while retaining a decent image quality for the target classes. You may be wondering, hey, this is so peculiar, who cares? Well, think of this example. Let's say you are going through a security scanner at an airport. Those terahertz waves are giving about a millimeter, sub-millimeter resolution to the inspector. Your entire body is seen with about a millimeter resolution. But nobody cares if you're fat, if you're thin. We care for weapons, right? Metal objects. So these kinds of class-specific imagers will erase obvious, unwanted, undesired classes of objects. They will be never recorded, and they will only create images of the targets of interest, so that you don't have to digitize everything. You don't have to store, upload images, only if there is a target of interest. You can also bundle the target to contain more than one class of objects. You can say, these are the classes of objects that I want to image, and the rest I want to erase. It also works for more complicated objects. This is a trouser imager erasing everything else, so that you can actually just have high fidelity reconstruction of the target objects, and the rest you erase. We formed an experimental demonstration of this in terahertz waves with a 3-layer diffractive processor. So the layers of the phase planes for the 3-layer diffractive processor are shown here. They were fabricated with a 3D printer and assembled as shown here to do imaging. And it works beautifully well for experimental results, giving you target objects imaged with valve fidelity and everything else undesired erased from the output field of view. One thing that is very exciting about a diffractive processor is that, unlike a metamaterial, the design of a diffractive processor will not change as you change the wavelength. If you go from a long wavelength to a drastically shorter wavelength, you don't need to design anything. You just shrink the diffractive layers according to the wavelength, and the refractive index of the material that you use will be defining the phase profile that you need to fabricate. That's a big advantage of diffractive processors. No redesign, just take it and move it to different parts of the spectrum. In fact, we have taken our designs and fabricated using 2-photon polymerization, smaller features so that we could operate at infrared 1.5 micron. And that these are the experimental results coming from IR radiation, where everything was approximately on the order of wavelength here, shrunk, giving you the idea that you can take designs and scale them to different parts of the spectrum purely based on stretching or expanding the features, nothing else. So far, I've been talking to you about diffractive processors working as optical computers in the analog domain. But arguably, a bigger opportunity here perhaps is their collaboration with digital AI. So diffractive networks and digital backend or digital neural networks, convolutional neural networks, for example, they form some beautiful collaboration for various different applications. I'll pick up 2 applications where I can highlight the impact of the collaboration between digital AI and the diffractive computing to give you best of both worlds, analog computing and digital computing. And these will be from first super resolution imaging using diffractive decoders, and the last part that I'll finish off with is going to be communication around opaque occlusions. So in this first demonstration of the utility of the collaboration between digital AI and diffractive computing, we're going to be targeting super resolution image displays. Think of the problem where you have a very high resolution image, but you don't want to send that high resolution image to a local device. Think of this as your AR, VR set. You can't send too much data per second. Well, this AI front end is going to compress the information, and diffractive decoding will decompress it so that you can actually have super resolution image here without a high resolution display and without consuming much power, so that you can do compressed information transfer. Think of it another way like this. We're forming a certain diffraction language between digital AI and diffractive decoding. So the front end is taking high resolution images, compressing them perhaps by an order of magnitude into low resolution barcode-like patterns, which, if you shine light through them with a spatial light modulator, you can actually decode with a fixed diffractive processor the super resolution image. Decoding is passive, speed of light, a few picoseconds in reconstruction speed. You save transmission, and you don't need high resolution displays. You can do low resolution displays. This system actually can give you space bandwidth product improvements on the order of anywhere between 9 to 16. K is the super resolution factor in each direction. This is the compression network, and this is the diffractive decoder. This is fixed, and this is also fixed, but they're jointly trained, which means these two, digital and diffractive decoder, can handle any arbitrary image compressed into this representation to be decoded by a physically fixed diffractive decoder that gives you a space bandwidth product improvement of about 16 in this case. If you don't do this trick, well, these are low resolution images with the same display that you would get, and that's showing you the super resolution factor. So this is actually fairly resilient. You can train a diffractive super resolution display with, let's say, 16-bit quantization, and then attack it with less bits. So which means you surprise the diffractive decoder here with reducing the bit depth of your encoder here. It stays fairly resilient down to approximately 6 to 5 bit depth. After, of course, 2-bit, you start losing reconstruction fidelity. But this is blinded ablation study, which means the diffractive decoder was trained here with 16-bit depth. So it's actually quite resilient in its performance. And you can bring color to these systems. That's the beauty of diffractive decoders. You can program them to project RGB patterns if they're trained accordingly. And the encoder here is taking any image at 3 channels and compressing them into a representation, phase representation that is specific to these wavelengths, which is instantaneously decoded. And you can see here that it's got a beautiful aberration, spectral aberration-free operation. You can resolve at different combinations of RGB with the same decoder that is trained. And again, this is not dispersion engineering here that we do. Diffractive phase encoding with the same material is our ingredient to make this happen. We've experimentally validated these by building diffractive processors. This is a 3-layer version of it. And it showed some beautiful experimental validation compared to the low resolution images. You've seen the super resolution factor. In this case, it's a space bandwidth product improvement of approximately 9-fold. We've also shown that you can work with a single diffractive layer in this case. These are with a single diffractive layer design, the same results, giving you also beautiful super resolution factor compared to the low resolution display that we have in front of the diffractive layer. In the final part, in the last 5 minutes or so, I will give you another flavor of this collaboration between digital AI and diffractive computing that are jointly trained. And in this example, we'll pass information through an opaque occlusion. Imagine the case where between your antenna emitter and between the receiving aperture, there's an occlusion. This is 100% absorbing, let's say. If you put a perfect camera in your aperture, you will miss it. And imagine the case where the occlusion is so large that no ray from your aperture can directly reach the collection aperture. So it's like there's no direct line of sight. How do you solve that problem? Well, a lot of people looked into this by using a wall, bouncing radiation off of a wall. Here, we're going to show that that's not necessary. The occlusion's edges actually act like secondary waves. The goal here is jointly train an electronic network that understands the topology of the occlusion and communicates with it such that any arbitrary message can be instantaneously almost mapped into a message phase code that is transmitted through the scattering of the edges to be reconstructed by the diffractive layers that are jointly trained with the encoder. These are not in isolation. Digital neural network and diffractive decoder are jointly trained with the fidelity of the output field of view giving you the message. And at the end, we form some beautiful reconstructions of messages that you want to pass through the edges of an opaque occlusion where there's no direct line of sight. So these are some numerical results. We have experimental evidence for this as well, but this is showing you external generalization. These types of objects were never used before. The encoders here are fixed. Decoders are diffractive. They're also fixed. Post-training, we're creating arbitrarily new messages. They're rapidly transformed into phase encoding, which uses these edges of the opaque occlusion to communicate with the output field. Look at this case, for example. This case highlights that there's no direct ray from your input aperture that can reach to the output aperture. Same here. In those situations, even, you can faithfully reconstruct. And you can think of this as communication by programming side scattering of an opaque occlusion. You may be wondering, well, probably this is a very inefficient process because no ray can directly reach the detection aperture. Well, you're right, and at the same time, wrong. You can program these diffractive processors to have some compromise in image reconstruction, structural similarity index measure, and diffraction efficiency. Depending on your loss function and how you tune it, you can have different topologies, which means if you don't like to work with low diffraction efficiency solutions, you can go up in here and have significantly higher diffraction efficiency with some compromise in structural fidelity. Look at this reconstruction, for example. It's 27.4% between the input and output aperture using side scattering. Yes, it's slightly lower resolution, but still you have a beautiful gain in diffraction efficiency. In fact, you can go up to 52.5% diffraction efficiency with some resolution loss. But all of these are cases where we don't have a full information channel because of the opaque occlusion, and we're using this side scattering from these samples. Experimentally, we've shown this system using an occlusion like this. This is aluminum, which blocks radiation. And through the aluminum, we were able to image beautifully in our experiments the messages that we wanted to pass through. If you were to have a perfect camera, this is what you would be seeing. Basically, the aluminum would be blocking the real message. And through side scattering with spherical wave and scattering potential engineering through phase space engineering, we were able to reconstruct these beautifully well for different test objects. This was a rectangular or a square aperture in this case, but you don't have just limitation. It can be any arbitrary topology. In fact, we've experimentally demonstrated with different kinds of topologies. This is an occlusion that is almost random looking, and it was unknown in this case. You can still reconstruct beautifully well with these peculiar and random looking designs of occlusions. In fact, this movie is highlighting how without knowing the exact boundaries of a dynamic occlusion, you can communicate. So the encoder digital network is fixed. Diffractive layers are fixed. There are 3 of them. They are jointly trained with the encoder. The dynamic occlusion is randomly evolving. Look at the stability of the images. Like you see some slow variations in the output, but despite the occlusion's dynamic evolution, you have a very nice stable reconstruction. If you make the occlusion bigger, like for example this, you start to lose more suffer more. So the resolution of the reconstructions of the decoder is going worse as the random dynamic occlusion is evolving. But still, it gives you the idea of the trade-off between resolution and the size of the occlusion and how you're completely bypassing a camera-based system through these spherical wave engineering systems. To sum up, to conclude, there's some beautiful collaboration between digital AI and diffractive networks. It's best of both worlds. Diffractive networks are supersets to traditional cameras because they can approximate any spatially varying point split function. Coherent, incoherent, temporally incoherent, spatially incoherent, and depending on your illumination, partially coherent, you can program them. And I think there are many exciting opportunities in this push-pull between diffractive computing and digital computing. So with this, I'd like to conclude and summarize that deep learning designed light matter interactions are really very exciting for computational imaging, camera design, statistical inference, and you can also think them of as inverse optical engines that you can program for various different tasks. With this, I'd like to conclude, acknowledge all of our funding agencies that are behind this work. And finally, I'd like to also say happy birthday to Advanced Photonics. I think the work that you and your editors have been putting together since 2019 is really inspirational, and wish you all the best in the next 5 years and the next 5 years of success. Thank you.
Thank you, Professor Ozcan, for the wonderful and interesting presentation. Here, I have a couple of questions from our audience. So the first question, thank you, Professor, for giving the inspiring talk. Apart from diffractive layers, matter surfaces also provide powerful light manipulation capacities. Can you briefly comment on the potential applications of matter surfaces for optical processing and computational imaging?
Thank you. That's a great question. In fact, if you are looking at a lengthy review about metasurfaces and diffractive layers, how they're working together or how they are covering different applications, we've recently published a perspective article in Nature Communications. If you haven't seen it, you can find it. It's called Diffractive Optical Computing in Free Space, Nature Communications, just came out last week. It's in collaboration with Dr. Nadir Engaita's group from UPenn. So, of course, Nadir is a pioneer in metasurfaces and using it for free space computing of all kinds. So from that perspective, hopefully, we wanted to give the message to the community about the amazing opportunities where metasurfaces, together with diffractive processors, can kind of work together to get the most out of material science and 3D fabrication for building free space processors of information. So, yeah, that's a very lengthy paper. I recommend you definitely to take a look at it if you haven't. At a top level, diffractive processors do not need to go below half a wavelength in their lateral feature size. They don't need material dispersion engineering. They don't need peculiar polarization responses. You can bring polarization universal transformations with diffractive processors with isotropic materials. You can find examples of that from our former work. Just like you can bring spectral processing power to a diffractive processor without any dispersion engineering. Flat dispersion, like n of lambda equals constant across a certain band. Even within that band, you can do exotic things at every wavelength independently. So it has some unique features. But of course, metasurfaces also bring some amazing advantages, especially in terms of its fabrication processes, approximating complex transmission coefficients with deeply sub-wavelength engineering of dielectric and plasmonic structures and/or and how you can, in a single lithography step, generate those, as opposed to doing multi-step phase approximations with diffractive layers. So there are pros and cons of each approach. And I argue that no matter what you do, you got to be able to cascade them. The power of surfaces is only going to shine when you can cascade them. What I mean by cascading is one layer following another layer at the diffraction limit of light, which means you must be accurate in whatever you're doing between two layers at a diffraction limit of light, because anything less accurate in high numerical aperture regions is going to cascade and give you errors at the exit aperture, and we cannot tolerate that. And that's something to think about. So I'll stop here and refer you to the recent Nature Communications perspective that we had with Engata Group from UPenn.
Okay, thank you. The other question is, since the optical and electronic processors feature different advantages, is it possible to further boost the interference performance through integration of optical computing with electronic computing?
Absolutely. I think the last two examples were highlighting some of that. So if I were to go back, pardon me, let me full screen this one. So if I were to go back to this slide, this was exactly kind of referring to that line of thinking. So if I want to pass a visual information, visual scene information to digital GPU-based processing based on, let's say, your favorite convolutional neural network architecture, you need a focal plane array, you need an optical system. Think of phase imaging. Let's say you are looking at cells that have phase signatures, or you're looking at reflections from pedestrians in the phase space, right, distance. In all of these cases, GPUs or your favorite electronic tools that are very successful today will only be applicable after some hardware, optical hardware, gives you information. Phase, I pick up phase because phase retrieval in optics is a very tedious, difficult task. It's a difficult hardware to get the phase information and reconstruct it. Only after that step, digital computation starts, right? So diffractive processes can harness those spatial features, modes of a scene, two-dimensional, three-dimensional, spectral, polarization, amplitude, all together, so that it actually delivers a compressed representation to your focal plane array, so that it does image compression, if you want, or reduction of dimensionalities of a polarization, spectral, and phase space that you have in front for classification, you name it. And I think that symbiotic relationship is the biggest. That means your camera, that is now a dummy camera. For centuries, we optimized cameras to be spatially invariant in their response. That perhaps is not the best way to communicate with back-end GPUs. And that's essentially what we're learning here. All of these examples that I've highlighted here on this slide is some example of it, and there are many others. And if you want to read more about this, I suggest this IEEE JSTQ paper from 2019 that actually did the first compression of spatial information for a classifier to act on it. So you can take, for example, a very primitive LeNet and do fantastic classification with 10 to 100-fold less number of pixels at the focal plane array. It shows you the integration with electronic computing and how analog computing can help for that.
Okay, I have a question about the say comparison between the AI training and diffractive network. For example, if we do the imaging processing using the AI models training, and is there any limitation if we transfer the model to the diffractive network? can you realize anything by
Okay.
optics?
Yeah, so that's a great question. So let's say there is a functional representation that let's say a ResNet is getting for a certain task. You cannot get the same functional representation with just a diffractive processor. First of all, architectures are different. Nonlinearity in optics-induced nonlinearity is very expensive. As a result, we don't have the luxury of having a diffractive processor and then putting a nonlinear layer and then having some additional diffractive layers, et cetera, because then you need to kind of go back to electronics, generate it, and then run it again. So if I'm going to go back and forth between electronics and optics, it's not a good architecture. So in that domain, I think you are losing the strengths of optical computing. So that means the functional representation that you can approximate with a diffractive processor is going to be a subset of what you can approximate with digital computing. However, digital computing starts with an image when it comes to visual scenes. So for visual scenes, if you want to act on the information, diffractive processors are probably a better way on acting the information and digitizing a representation to be performed by backends. So it's the best of both worlds that will probably make a better visual processor all in all. If purely in the mathematical domain, if you're targeting function approximation power of a digital neural network, they're universal function approximators. Diffractive networks are not universal function approximators. You can argue by cascading them with many nonlinear detectors and then gating them, you can approximate better functions. We call them ensemble learning, which means you take a bunch of diffractive processors, each of which ending with some intensity detectors, nonlinear intensity detectors. You encode the information in the phase space. That gives you sufficient representation to approximate, harder to approximate or achieve functions, and you improve your generalization. Yes, but still there's a huge gap between what a purely digital network can do and a diffractive network can do. And mostly it's because of the expensive nature of nonlinearities in a cascaded form.
Okay, so a further question, you just mentioned the nonlinearities could be a more expensive issue. Then what about the incoherence?
Yeah, incoherence, we have, so we have already shown basically, let me go to this slide here, pardon me. So first of all, for temporal incoherence operating with a large bandwidth, we can do that. So here we're programming, for example, the diffractive processor to act on a few hundred different wavelengths all in parallel and executing different transformations. So you can actually utilize the free space rate propagation between diffractive layers and the phase kernel as a way to approximate different transformations at different wavelengths. So you can handle temporally incoherent radiation and program diffractive processors. When it comes to spatially incoherent, we have shown that basically there is a beautiful relationship between a spatially coherent diffractive processor and it is spatially varying point spread functions, coherent point spread functions, and how they are related if you were to switch the same diffractive architecture to spatially incoherent mode. In that case, the intensity point spread functions are actually becoming the intensities of the coherent point spread functions, which means, stated differently, we've shown you can approximate any intensity linear transformation between an input and output aperture at a diffraction limit using a spatially incoherent illumination. In fact, if you know the transformation function or the spatially varying point spread functions, you can design it coherently and switch the wavelength or switch the illumination to incoherent for it to approximate those functions for you. So this is actually explained in this paper that we published in 2023, which also relates spatially varying coherent point spread functions to spatially varying incoherent intensity point spread functions.
So this LSA paper is a experimental presentation or numerical?
This is a numerical analysis of showing you how you can program it for any arbitrary intensity transformation. And showing the relationship between coherent, spatially coherent and spatially incoherent illumination.
Mm-hmm. Okay. Due to the time constraint, maybe the live streaming is terminated now. And thank you very much again, Professor Ozcan, for the great and interesting presentation.